Hello everyone and welcome back to Math Made Easy. In the previous lecture, we studied the Gauss-Seidel iterative method for solving systems of linear equations. We saw that Gauss-Seidel generally improves upon the Jacobi method because it uses the newly calculated values immediately within the same iteration. But now let's just ask an important question. Can we make Gauss-Seidel converge even faster? In many cases, the answer is obviously yes. And this leads us to the today's topic as successive over-relaxation method, commonly known as SOR method. The SOR method is an extension of Gauss-Seidel method and it introduces an additional parameter called as relaxation factor, denoted by omega. So by choosing an appropriate value of omega, we can sometimes accelerate the convergence of the iterative process significantly. However, choosing omega incorrectly can also make the method converge more slowly or even cause the divergence. Therefore, the understanding the role of this parameter is extremely important. In today's lecture, we will understand the idea behind relaxation, derive the SOR formula, discuss the role of omega and learn the algorithm and the convergence consideration and solve a complete numerical example. So let's just begin. Firstly, just recall what happens in Gauss-Seidel. Suppose the Gauss-Seidel method gives us a newly calculated value as is xi k plus 1 gs. And this Gauss-Seidel method simply accepts this value as is xi k plus 1 equals to xi k plus 1 gs. But what if is this value is not the best possible step towards solution? What if we could control how much of the new correction we actually use? And this is a basic idea about relaxation. So instead of accepting the Gauss-Seidel value completely, we combine the old value with the newly calculated Gauss-Seidel value. So we write it as this xik plus 1 equals to 1 minus omega times xik plus omega times xik plus 1 gs, where this omega is the relaxation factor and this is the fundamental SOR formula. And the value of omega determines how aggressively we update the solution. Here are three important cases. And first case will be omega value as 1. Now substituting this value in this xik plus 1 equals to 1 minus 1 xik plus 1 into xik plus 1 gs. Therefore, that becomes this xik plus 1 equals to xik plus 1 gs. So when omega equals to 1, SOR becomes exactly the Gauss-Seidel method, and that is a very important result. Now the second case will be from omega value lying between 0 and 1, and this is called under relaxation. We deliberately move less aggressively towards the newly calculated value. For example, if I take omega value as 0.5, the next ik plus 1 becomes 0.5 xik plus 0.5 xik plus 1 gs. Now under relaxation can be useful when a system is sensitive or when a more conservative update is desirable. Now the third case is we can take this omega value between 1 and 2, and this is called the over relaxation. Here we move more aggressively towards the new value. For example, we can take this omega value as 1.5, and this can significantly accelerate convergence for suitable systems, and that is why this method is called successive over relaxation method. For the standard SOR method, we generally consider omega value between 0 and 2. But don't make the mistake of thinking like the larger omega is, the faster the method will always be. And that is not true. The optimal value depends on the particular system, and a poorly chosen relaxation factor can actually make the convergence slower or may cause the divergence as well. So just consider the system here is as a11 x1 plus a12 x2 up to a1n xn equals to b1. Now solving for x1, we get this x1 gs value as 1 by a11 into b1 minus summation A1j xt, where j is starting from 2 to n. And this SOR modifies this Gauss-Seidel value as this x1k plus 1 equals to 1 minus omega x1k plus omega times x1gs. Similarly, for the general ith variable, we get this xik plus 1 is equals to 1 minus omega times xik plus omega by a I multiplied by bi minus summation aij xjk plus 1, where j is starting from 1 up to I minus 1, minus summation aij xjk, where j is starting from I plus 1 up to n. And this is the SOR iteration formula. Now notice that it contains the same updated and old values used by Gauss-Seidel, and the only difference is the additional relaxation factor omega. Now let's just understand this formula intuitively. Suppose the previous approximation is xk equals to 2, and the Gauss-Seidel calculation gives you this xgs value as 3. And if omega value is 1, we can take this xk plus 1 as 3. Now suppose if we have omega equals to 0.5, then this xk plus 1 becomes 0.5 multiplied by 2 plus 0.5 into 3. That gives you 2.5. So we are taking only part of the correction. Now suppose omega value is 1.5. Then this xk plus 1 becomes 1 minus 1.5 into 2 plus 1.5 into 3. And hence become this 3.5. So we have moved beyond the Gauss-Seidel value now. And this is known as the over-relaxation. So this SOR algorithm can be summarized as follows. Like, we start with this writing the system as ax equals to b, then check an appropriate convergence condition. For many university type of problem, strict diagonal dominance is useful sufficient condition. Now just rewrite the equation to isolate each of the variable. Choose your initial approximation as is x naught and y naught and z naught and up to so on. Then choosing a relaxation factor omega between the 0 and 2. Now calculate each new variable using the latest available values and apply the relaxation factor and repeat until the stopping criteria is satisfied. Now just solve the system as is 10x plus y plus z equals to 12, 2x plus 10y plus z equals to 13, and it's 2x plus 2y plus 10z equals to 14 using the SOR method with omega given as 1.1 and the initial approximation x0, y0, z0 as 0, and obtain the solution correct up to 3 decimal places. For that, we need to check for the diagonal dominance, where this first row having this 10 is greater than 1 plus 1, and in the second row we have this 10 greater than 2 plus 1, and in the third row we have this 10 is greater than 2 plus 2. Therefore, the matrix is strictly diagonally dominant. And we already know that this xgs equals to 12 minus y minus j whole divided by 10. And this ygs equals to 13 minus 2x minus z whole divided by 10. And zgs equals to 14 minus 2x minus 2y whole divided by 10. Now we apply the relaxation now. So we have this SOR formula for the x, where this xk plus 1 equals to 1 minus omega xk plus omega times 12 minus yk minus zk whole divided by 10. And since this omega value is 1.1, so we get this xk plus 1 as minus 0.1 xk plus 1.1 times 12 minus yk minus zk whole divided by 10. Now remember that this Gauss-Seidel uses a new x immediately. Therefore, you get this y, k plus 1 equals to minus 0.1 yk plus 1.1 times 13 minus twice of x k plus 1 minus zk divided by 10. Now using the both new values for the z, we get this zk plus 1 as minus 0.1 zk plus 1.1 times 14 minus twice of xk plus 1 minus 2yk plus 1 whole divided by 10. And with the iteration 1, we have get these x1 value with the initial values as 0. We get this x1 value as minus 0.1 times 0 plus 1.1 into 12 by 10, and hence got this as 1.32. And again, using the new x1, we get this y1 as this 1.1 times 13 minus twice of 1.32 whole divided by 10, and hence got this is 1.1396, and hence z1 value as 1.1 times 14 minus twice of 1.32 minus twice of 1.1396 whole divided by 10, and hence get is 1.038488. Now with the iteration 2, we get this x2 value as 0.964710, and this y2 as 0.997739, and z2 value as 1.000658. Now we already can see that the values are already moving very close to these 1. So the iteration converges towards this 1, 1, 1, and hence we got the answer as x equals to 1, y 1, and z equals to 1. Now notice something interesting, like our first SOR iteration produced as x1 equals to 1.32, which actually goes beyond the exact solution as x equals to 1, and that is not necessarily a problem. Remember, we deliberately chose this omega value is greater than 1. So we are over relaxing the iterations. And the objective is not necessarily to make every individual approximation closer to the answer. The objective is to make the overall sequence converges faster. And this is an important conceptual point. Now the point comes for the stopping criteria. So we can stop when this maximum of this mod value of xik plus 1 minus xik is lesser than epsilon. And for the 3 variables, we can take this maximum value of mod of xk plus 1 minus xk, mod value of yk plus 1 minus yk, and the zk plus 1 minus zk, which should be lesser than epsilon. And this tolerance epsilon should be chosen according to the accuracy specified in the equation. So today we studied the SOR, Successive Over-Relaxation method. We saw that SOR is an extension of the Gauss-Seidel method, in which we introduced a relaxation factor omega to control how aggressively each new approximation is updated. We discussed the 3 important cases, as is omega lying between 0 and 1 for under relaxation, omega 1 which gives us the Gauss-Seidel method, and omega between 1 and 2 for over relaxation. We derived the SOR iteration formula, developed the algorithm, and solved a complete numerical example using an iteration table. And the most important thing to remember is that choosing omega appropriately is crucial. A suitable value can accelerate the convergence, while a poor choice can make the method slower or even may cause the divergence. With SOR, we have now completed the major iterative methods listed in our roadmap, that is Jacobi to Gauss-Seidel and up to SOR. In the next lecture, we will move to another important method for solving systems of linear equations, the Thomas algorithm for tridiagonal systems. We will first understand what a tridiagonal matrix is and why such systems have a simple special structure, and how this structure helps us to solve them much more efficiently than a general system. So thank you for watching, and if you found this lecture helpful, don't forget to like and share with your classmates and subscribe to Math Made Easy. And I'll see you in the next lecture.